Hello everyone, welcome back to the online lecture series of fluid mechanics. Today will be our fourth lecture and today's topic of discussion will be properties of fluids. Now the properties may be of different kinds. It may be physical property or it may be thermodynamic properties, chemical properties, electrical properties or magnetic properties, etc. Mainly what we are going to discuss here is the physical or material properties of fluids. So what are the various physical or material properties? Physical or material properties of fluids. First, in the first category we will see the properties which characterizes the heaviness of the fluid, and this includes mass density, weight density, and third is specific gravity. Second, we have the properties which characterizes the flow behavior of fluids. Now this mainly includes a very important property which is known as viscosity. Here we will be seeing two types of viscosity. First is the coefficient of dynamic viscosity, also known as absolute viscosity, and second will be the coefficient of kinematic viscosity. In the third category, we will see the properties which characterizes the formation of interface in case of fluids and some associated phenomena. So this category will include property which is known as surface tension, and the coefficient of surface tension, it is denoted by the letter sigma, and the associated phenomena of capillarity. This you might already be aware of. We have already learned in school about capillary rise and capillary fall. So it is the same thing, and but here we will include some more interesting phenomena that are associated with the interfacial phenomena that are associated with the formation of interface in case of fluids. So, and the fourth category includes another important property which is called vapor pressure, and one associated phenomena which is called cavitation. Now, while doing the properties which characterizes the heaviness of fluids, we will also encounter two important properties. First is known as the the bulk modulus of compressibility, or the simply you can say compressibility, and the second one is the coefficient of volumetric expansion. Now remember here what we will do, we will learn about the different properties of the fluids, as well as we will also see how these properties may change with change in temperature and pressure. Now we know that materials have definite mass and volume at a given temperature and pressure. So let us consider a given volume of fluid at a specific temperature and pressure. So for that given volume, the property that characterizes the mass of the fluid is known as mass density. So our first property is mass density. This is denoted as rho, and it is defined as mass per unit volume. So we have rho, which is equal to m upon v. From here we can calculate the mass as rho into v. The SI unit of mass density, see the SI unit of mass is kg, and for volume we have meter cube. So the SI unit of mass density is kg per meter cube. If you use CGS system, the unit will be gram per centimeter cube, and in case if we use British gravitational unit, it is slugs per cubic feet. Now in some books you may find various numericals where the unit for density is given as slugs per feet cube. So it is important to know what this slugs per feet cube means. Actually, one slug, the mass of one slug is equal to 32.174 lbm. 32.174 lbm, which is pound mass. So if it is given in slugs per feet cube, how we are going to convert it into kg per meter cube? For that we have a conversion, 1 slug per cubic feet. This in terms of kg per meter cube, this is equal to 515.4 kg per meter cube. Now see, the inverse of mass density is also a property which is mainly used in thermodynamics. We call it specific volume. So we have a specific volume which is denoted by small v, and which is equal to volume per unit mass. So this specific volume V is nothing but the reciprocal of our mass density. Now let us see the different density of some of the common fluids that we encounter. Now the common fluids which we encounter generally, what are those common fluids? We have water, then we have mercury, we have acetone, ethanol, methanol. So let us see what are the values of the density of these common fluids. We will also see the values of liquids as well as for gases. Now some common liquids are, first is mercury. Now remember, we are seeing the property, the density value is at 1 atm pressure and 20 degrees Celsius. As I have told you earlier, materials exist at a specific temperature and pressure in a definite state. So we are going to see the density of some of the fluids at 1 atmospheric pressure and 20 degrees Celsius. First is mercury. Now the density of mercury is quite large. It is about 13,550 kg per meter cube. 13,550 kg per meter cube. Then we have glycerin, which is also quite denser, and it is having a density of 1260 kg per meter cube. Now third is our water. Rather we will see seawater, because seawater is generally more heavier than our normal water. So if we see seawater of 30% concentration, the density of this is higher than the normal water, and it is equal to 1025 kg per meter cube. Now the water is having a density of 998 kg, rather it is 995 kg per meter cube, because here we are taking a temperature of 20 degrees Celsius. So the density of water at 1 atmospheric pressure and 20 degrees Celsius is 995 kg per meter cube. For seawater, for uh, SAE oils, 50W oil, this is also quite denser and it is having a value of 902 kg per meter cube. These are basically the Indian oils that we use. So we have one more category, SAE, say it comes in various categories, 50W oil, 30W oil, 10W oil. So let us see 10W oil. So 10W oil, the density is 870 kg per meter cube. Additionally, we also have some density of some common other substances such as kerosene, which is 804. We have methanol, which is 792, and ethanol, which is 789. Similar to common liquids, we shall also note down some of the density of common gases that we encounter. So let us see the density value of some common gases. For density of gases, here we will take 1 atmospheric pressure and 0 degrees Celsius. Now, amongst the common gases, the most denser one is carbon dioxide, and it is having a relatively high density value, which is equal to 1.96 kg per meter cube. Now, another life-sustaining gas is our oxygen, and it is also having a relatively higher density value than the air that is going everywhere, because the density of air, it is equal to 1.23 kg per meter cube. Next is nitrogen. For nitrogen we have actually it is 1.29. For nitrogen we have 1.25 kg per meter cube. Now, similar to nitrogen, we have carbon monoxide, and it is you can say it is having equal density value than nitrogen. It is actually 1.249 kg per meter cube. Next is the methane gas. The density for methane gas is 0.7158. 0.7158 kg per meter cube. And lastly, we have the hydrogen, the lightest one, and it is equal to 0.0899 kg per meter cube. So you can see that it is the hydrogen is the lightest one in this group, and carbon dioxide is the heaviest one in this. Now, see the measurement of mass density for liquids, it is quite simple, and even for solids. But in case of gases, the measurement is quite involved. Now, the characteristic equation of gases can be used as a means for calculating the density of can be used as the basis for calculation of density of gases. Now, what is this characteristic equation of gas? We know that the characteristic equation for gases, it is actually derived from the various gaseous laws that we have. What are the various gaseous laws? You might be familiar with the Boyle's law, Charles' law, Avogadro's law. So combining these laws, we get a characteristic equation of gas. Let us recall it. So first gaseous law is the Boyle's law. Now, according to the Boyle's law, we know that at constant temperature, the pressure is inversely proportional to volume. So Boyle's law says Boyle's law at constant temperature we have P at constant T we have P inversely proportional to volume. Now second is the Charles law. Here we take at constant pressure we have the volume V is directly proportional to temperature. And third, we have Avogadro's law. It states that at constant temperature and pressure, the volume is directly proportional to the N, where N stands for number of moles of the gas. Now, combining the three equations with the characteristic gas equation, which is PV is equal to N R U T. Here RU stands for the universal gas constant. So this universal gas constant will be used for our characteristic gas equation, and for other gases we have an alternative form, alternative equation, which is PV is equal to mRT. Now in this case, this R stands for the specific gas constant. For the gas which we are considering, it will have a specific gas constant value. So we have PV is equal to mRT. Now using this equation, PV is equal to mRT, we can easily calculate the density of for gases. As you can see, PV is equal to mRT, or P will be equal to m upon V R T. Now we have already defined the mass per unit volume as density. So instead we can write this as rho R T. So we have P is equal to rho RT, and from here we can calculate the value of rho as P upon RT. Now depending on the specific gas constant for the particular gas, we will have a particular value of R, and at a specific pressure and temperature we can easily calculate the value of density for that gas. Now it also depends on the various processes such as isothermal process or adiabatic process. We will discuss on the topic later. So this was about the density of fluids. Now we have discussed the mass density of fluid. Now one more property is the weight density of fluids. Now weight density of fluids, it is defined as the weight density may be denoted by small w, and it is nothing but the ratio of weight upon volume, or w upon v. Now we know that the w is equal to m into g, so we have small w is equal to mg upon v. Now here m upon v, we have already defined this as the mass density, so this becomes rho g. So the weight density W is equal to rho into G. Now suppose for water, if we take water at 4 degrees Celsius, the density of water at 4 degrees Celsius, it is around 1000 kg per meter cube. So how to calculate the weight density of water at 4 degrees Celsius? So weight density of W for water at 4 degrees Celsius will be equal to the rho into G. So it is equal to 1000 into 9.81, and of course the unit is Newton per meter cube, because the unit of weight is Newton and for volume we have meter cube. So SI unit is Newton per meter cube. So this comes 9810 Newton per meter cube. So if we know the mass density of the fluid, we can calculate the weight density by simply multiplying it with the acceleration due to gravity value, which is 9.81 meter per second square, and we will get the value of W. Now we have one more property characterizing the heaviness of a fluid, which is known as specific gravity. So let us discuss about specific gravity. Specific gravity is actually a non-dimensional parameter to that is used to compare the density of fluids, because specific gravity is also known as relative density. Specific gravity, it is denoted as Sg, and it is also known as relative density. So, or Rd. Now, this specific gravity is simply defined as the ratio of the mass density of the fluid upon the mass density of a standard fluid. So what is this standard fluid? This is standard fluid. In case of liquids, for liquids, the standard fluid is water. We'll take density of water at 4 degrees Celsius and 1 atm pressure. And for gases, the standard fluid will be air at standard temperature and pressure. Now, since this is the ratio of densities, so obviously this is a unitless property or a non-dimensional property, so there is no unit. So it is unitless. So let us see the specific gravity value. How to calculate the specific gravity of water? Specific gravity of water at say 20 degrees Celsius. Now we know that the rho of water at 20 degrees Celsius, it is equal to 998 kg per meter cube. So the specific gravity of water may be calculated as the rho of water at 20 degrees Celsius and upon the density of the standard fluid. In this case, it is water only at 4 degrees Celsius. So we have rho of H2O at 4 degrees Celsius. So it is equal to 998 upon 1000. So it is equal to 0.998. So the specific gravity of water at 20 degrees Celsius, it is 0.998. And if you need to find out the specific gravity of water at 4 degrees Celsius, what will be the value of Sg? Sg will be equal to the density of water at 4 degrees Celsius upon the density of water at 4 degrees Celsius. So both in the numerator and denominator we have 1000 kg per meter cube. So specific gravity of water at 4 degrees Celsius is 1.